Did you know that every star you see in the night sky, every planet orbiting a distant sun, and every single thing you have ever touched are all made from the same fundamental ingredients? This is not just poetry, it is a profound scientific truth. These ingredients are the elements, the basic building blocks of our universe, and humanity has created a map to understand them all. The periodic table. It is more than just a chart hanging in a science classroom. It is a cosmic storybook, a guide to the stuff of existence itself. This essay will be your guide to that map, demystifying its symbols and revealing the elegant order hidden within. We will navigate its rows and its columns, explore its families, and uncover the patterns. Before we can read the stories written in the periodic table, we must first understand its language and layout. At its heart, the table is an organized chart of elements. An element is a pure substance consisting only of atoms that all have the same numbers of protons in their atomic nuclei. The tiny, fundamental particle of an element is the atom. Think of hydrogen, think of carbon, think of gold. The table's entire structure is built upon one crucial number. The atomic number. It is the atom's unique identification code. The table is meticulously arranged in increasing order of this atomic number, starting with hydrogen, atomic number 1, in the top left corner, and moving from left to right. As you move from one box to the next along a row, the atomic number increases by 1. This simple, sequential ordering is the key that unlocks all the table's secrets. This progression reveals repeating patterns, or periodicity, in the element's properties. The horizontal rows are called periods, and the vertical columns are known as groups or families. Each of these structural features tells us something important about the elements within it. Let's look closer at the periods. There are 7 periods in the standard periodic table, each representing a new principal energy level, or electron shell. The vertical columns or groups of the periodic table are where its predictive magic truly shines. Think of them as families, where each member shares common characteristics. Let us meet a few of the most famous families. On the far left in Group 1, we find the alkali metals. Sodium, Na, potassium, K, lithium, Li, rubidium, Rb, cesium, Cs, francium, Far. These metals are exceptionally reactive, so much so that they are never found in their pure form in nature. They react vigorously, sometimes explosively, with water. They are also incredibly soft for metals. You could cut pure sodium with a butter knife. Their family trait is having a single electron in their outermost shell, which they are very eager to give away in chemical reactions. Right next door, in Group 2, are the alkaline earth metals. Magnesium, Mg calcium, Ca beryllium, B, strontium. Senior like their neighbors in Group 1, they are reactive metals, but slightly less so. They have 2 electrons in their outer shell that they tend to lose in reactions. Calcium is the famous component of our bones and teeth. Magnesium is vital for hundreds of biochemical processes. They consistently form ions with a +2 charge, a predictable behavior that chemists rely on. The periodic table isn't just organized by numbers and families, it also has a clear geographical divide that separates elements into 3 broad categories: metals, nonmetals, metalloids. The vast majority of elements are located on the left side and in the center of the table, and are metals. When you think of a typical metal, you probably imagine something shiny, solid, strong, good conductors of heat and electricity, malleable, hammered into sheets, ductile, drawn into wires. Iron, Fe, copper, Q, aluminum, Al, gold, Au, silver, Ag. On the other side, clustered in the upper right corner, are the nonmetals. Their properties are generally the opposite of metals. They are typically poor conductors. At room temperature they can be solids, carbon C, sulfur, S, a liquid, bromine, Br, or gases, oxygen, O, nitrogen, N, chlorine, Cl. These elements are essential to life and our atmosphere. Running diagonally between these domains is a staircase-like line. Elements along this line are called metalloids, fence-sitters, a mix of properties from both sides. Their most famous property, they are semiconductors of electricity, can be controlled to conduct under certain conditions and act as insulators under others. The most famous metalloid is silicon, Si. Pure silicon powers our electronics. Other metalloids, boron, B, germanium, Ge, arsenic, As. Understanding this 3-way split gives a high-level overview of the chemical landscape. One of the most elegant patterns revealed by the periodic table relates to the physical size of atoms. When we talk about atomic size, we're referring to the atomic radius, distance from nucleus to outermost electron shell. You might think heavier atoms must always get bigger. The periodic table shows a more nuanced reality. The trend changes two ways, down a group or across a period. First, trend down a group. Atoms get larger as you descend a column. Lithium is smaller than sodium. Sodium is smaller than potassium. Each row down adds a new electron shell. That shell sits farther from the nucleus, increasing atomic size like adding another ring to a bullseye. Now the counterintuitive part, across a period. Move left to right, and atoms get smaller, even with more protons and electrons. Across a period, you add protons to the nucleus, and electrons to the same outer shell. More protons mean a stronger pull, drawing electrons closer and shrinking the radius, like a stronger magnet pulling filings. Two simple rules: size increases going down a group, it decreases going left to right across a period. Largest atoms live toward the bottom left of the table, the smallest live toward the top right. Beyond just size, the periodic table beautifully predicts how reactive an element will, that is, its tendency to participate in chemical reactions. Reactivity is the essence of chemistry. It's the drive for atoms to bond and form molecules. This drive is all about achieving stability. A full outer shell, like the noble gases. Atoms will lose electrons. Atoms will gain electrons. Atoms will share electrons. For metals on the left side and in the center of the table, the strategy is to lose electrons. Down a metal group like the alkali metals, reactivity increases. Potassium is more reactive than sodium. Cesium at the bottom is most reactive. Larger atoms down a group put outer electrons farther from the nucleus. Easier to lose. For nonmetals on the upper right, it's the opposite. Up a nonmetal group like the halogens, reactivity increases. Fluorine at the top is the most reactive nonmetal. Metals, reactivity increases down the table. Nonmetals, reactivity increases up the table. Noble gases, with full shells, are least reactive. Closely related to reactivity is another crucial trend called electronegativity. Electronegativity measures how strongly an atom attracts electrons in a bond. Think of it as electron greediness. While reactivity asks whether an atom will react, electronegativity asks how it behaves inside the bond. Does it pull shared electrons toward itself, or let them be pulled away? Electronegativity increases left to right across a period. Atoms on the left want to lose electrons, so they have low electronegativity. Atoms on the right want to gain electrons, so they have high electronegativity. Down a group, electronegativity decreases. Larger atoms with more shielding attract bonding electrons less. Overall, lowest in the bottom left, highest in the top right. Francium is lowest, fluorine is highest. Noble gases are usually excluded since they rarely bond. When two atoms have very different electronegativities, the high one steals an electron, forming an ionic bond. When electronegativities are similar, they share electrons, a covalent bond. This idea is hugely useful across chemistry and material science. The periodic table is far from being a purely academic tool confined to laboratories and textbooks. Its principles and the properties of the elements it describes are woven into the very fabric of our daily lives, our technology, and our bodies. Every time you use your smartphone, you are holding a miniature periodic table. The screen contains indium and tin. The battery contains lithium. The processor is made from painstakingly purified silicon. Engineers use knowledge of conductivity, strength, reactivity to select the perfect material for each tiny component. Your body is a complex chemical factory, and elements from the periodic table are its essential workers. Calcium forms bone structure. Iron sits at the heart of hemoglobin, carrying oxygen to cells. Sodium and potassium enable nerve impulses. Doctors use barium for imaging and lithium for mood stabilization, relying on predictable chemical behavior. Fireworks paint the sky with element fingerprints. Strontium red, copper blue-green, sodium yellow-orange, from chlorine in water to aluminum in aircraft, nitrogen and phosphorus in fertilizers, tungsten in old bulbs, and helium in balloons. The elements shape our world. We have journeyed across the chemical map of the universe, from reactive metals on the left to stable noble gases on the right. Ordering by atomic number reveals patterns in size, reactivity, and electronegativity. The table is a logical, elegant system of families and trends. Remember, 1. Atomic number defines identity and position. 2. Groups share valence electron behavior. 3. Periods track shells and smooth property trends. Adopt a simple habit. Learn one element each week. Name, symbol, one fact, where it's found, what it's used for. Small steps build mastery. The periodic table is the blueprint of matter. Learn the blueprint, and you will forever see the world in a new light.